Hello students, let us start with part 11 of equilibrium. Today we are going to start with the topic solubility equilibrium and solubility product. If a sprangly soluble salt like AgCl is stirred with water, only a small amount of it goes into the solution while most of the salt remains undissolved, but little amount of salt dissolves. It gets completely dissociated into ions. When a sprangly soluble salt is added to water, there exists a dynamic equilibrium between the undissolved solid salt and the ions, which is furniture in solution. At equilibrium, the solid AgCl continues to dissolve at the same rate at which the opposite process of precipitation takes place. Now AgCl gives Ag plus and Cl negative. So solubility product constant, that is Ksp, is equal to molar concentration of Ag plus and molar concentration of Cl negative, where Ksp is the solubility product and is equal to ionic product. So molar concentration of Ag plus, molar concentration of Cl negative for a saturated solution. Now BaSO4 solid, it dissociate as barium plus 2 and sulfate minus 2 and sulfate ion. So Ksp will be molar concentration of barium ion multiplied with molar concentration of sulfate ion. Similarly with silver thiocyanate AgSCN, we can also write its Ksp value. For an electrolyte MyXZ type, the equilibrium can be written as MyXZ, it gives Ym raised to power Z positive, means the ions separated, and Zx Y raised to power minus. Solubility product may be written as Ksp is both ions with their molar concentration, each raised to power their stoichiometries, where Y and Z represent number of ions in the formula of electrolyte. Solubility product of an electrolyte at a specified temperature may be defined as the product of molar concentration of its ions in a saturated solution. Each concentration raised to the power equal to the number of ions produced on dissociation of one molecule of electrolyte. Now, difference between solubility product and ionic product. Solubility product is the concentration of ions of electrolyte, each raised to the power of their coefficients in the balanced chemical equation in saturated solution. It is applicable only to saturated solution. At constant temperature, its value is constant for the given electrolyte. Now coming to the side of ionic product, it is the product of concentration of ions of electrolyte, each raised to the power of coefficients in the balanced chemical equation in the solution at any concentration, applicable to all types of solution, and its value keeps on changing with concentration. Now how to determine solubility product. The solubility product of sprangly soluble salt at a particular temperature can be calculated from a knowledge of solubility of the salt in water at that particular temperature. Next topic is common ion effect. If to an ionic equilibrium of the type AB to give A positive and B negative, a salt containing a common ion is added, the equilibrium shifts in the backward direction. This is called common ion effect. Acetic acid, being a weak acid, ionizes to a small extent as CH3COH. It dissociates as CH3CO negative and H positive. To this solution, suppose the salt of this weak acid with the strong base is added. It ionizes almost completely in the solution as follows and provides the common acetate ions. Taking example of sodium acetate, CH3COONA, it dissociates as CH3CO negative plus Na positive. if the concentration of CH3CO negative ions increases, and by Le Chatelier's principle, the dissociation equilibrium shifts backward to the solution of weak base like ammonium hydroxide, ammonium chloride is added, which provides the common ammonium ions. Dissociation of ammonium hydroxide is suppressed. Now taking example of ammonium hydroxide and ammonium chloride, they dissociate in a very simple way as usual. To the solution of silver chloride in water, if NaCl is added, which provide the common Cl negative ions, the solubility AgCl decreases. Means AgCl, it decreases as Ag plus and Cl negative. NaCl dissociate as Na positive and Cl negative. If to the solution of Sprengli soluble salt, if a soluble salt having common ion is added, the solubility of the Sprengli soluble salt further decreases. Now start with the topic buffer solution and buffer action. What is buffer solution? A buffer solution is defined as a solution which resists any change in its pH value even when small amount of acid or base are added to it. Types of buffer solution. Number 1. Solution of single substance. Solution of mixtures. Starting with single substance, the solution of the salt of weak acid and weak base. Solution of mixtures, acidic buffer and basic buffer. Acidic buffer is the solution of mixture of weak acid and salt of weak acid with strong base. For example, acetic acid and sodium acetate. Basic buffer. It is the solution of mixture of weak base and a salt of this weak base with a strong acid. For example, ammonium hydroxide and ammonium chloride. Now what is the buffer action? The property of a buffer solution to resist any change in its pH value even when small amount of the acid or the base are added to it is called buffer action. Here is the mechanism of buffer action. First is acetate buffer. CH3CONA, it gives CH3CO negative and Na positive. If we take acetic acid, it dissociates into acetate ion and H positive. If 1 mole of NaOH is added to acetic acid, then it gives CH3CO negative and water. And if 1 mole of HCl is added to acetate ion, then it gives back acetic acid. Buffer action of ammonium acetate solution. Ammonium acetate is almost completely dissociated in the aqueous solution as acetate ion and ammonium ion. In the solution, there is excess of acetate ion and ammonium ion. When a few drops of an acid are added to the above solution, the H3O positive ions given by the acid combine with the acetate ion to form weakly ionized molecule of acetic acid. This acetate ion then combine with hydronium ion to give back acetic acid and water. The H3O positive ion concentration of solution does not change practically and hence the pH of solution remains almost constant. When a few drops of base are added to the above solution, the OH negative ions given by the base combine with ammonium ion. The OH negative concentration and hence the H3O positive ion concentration of pH remains almost constant. Now buffer action of acidic buffer. Let us consider the buffer action of acidic buffer containing acetic acid and sodium acetate. As usual, they dissociate into their ions. By common ion effect, the ionization of acetic acid is further suppressed. Thus in the solution, there are excess of acetate ions and small amount of H3O positive ions. When a few drops of an acid are added to the above mixture solution, the H3O positive ions given by the acid combine with acetate ion. The H3O positive ion concentration and hence pH of solution remains constant. When a few drops of base are added, the OH negative ions given by base combine with H3O positive ion. As H3O positive ions are consumed, the equilibrium 1 shifts toward right. 1 equilibrium means the first reaction. More of acetic acid dissociate to make up the loss of H3O positive ion. Hence the H3O positive ion concentration or pH of solution does not change. Now buffer action of basic buffer. The buffer action of basic buffer can be explained by taking example of ammonium hydroxide and ammonium chloride. By common ion effect, the ionization of ammonium hydroxide is further suppressed. Thus there is excess of ammonium ion and small amount of OH negative ion. When few drops of a base are added, OH negative ion given by it immediately combine with NH4 positive ions and it give back ammonium hydroxide. The H3O positive ion concentration or pH of the solution remains unaffected. When a small amount of acid is added, the H3O positive ion given by its combine with OH negative, they proceed as the equation 1. As the OH negative ions are consumed, the equilibrium shifts in the forward direction. The H3O positive ion concentration or pH of solution remains fairly constant.